everyone. In this section, we introduce the Fermat theorem. Our discussion can be motivated by the problem of modular exponentiation reduction. More precisely speaking, let us assume that n is a positive natural number, a is a given integer, and m is also a positive natural number, which is typically really huge. Our mission is to simplify the expression a to the power of m modulo n. In other words, we're looking for an integer of smaller amplitude that is congruent to a to the power of m modulo n. Of course, one evident approach is to first compute the exact value of a to the power of m. From there, we can apply the division algorithm by taking n to be the divisor and find the remainder r, which is of course congruent to a to the power of m modulo n. However, in practice, the computation cost of this approach might be too expensive. On the other hand, assume that we're lucky enough that we found a positive natural number k satisfying that a to the power of k is congruent to 1 modulo n. Now we can apply the division algorithm by taking m to be the dividend and k to be the divisor. This results in m is equal to k times q plus r, where r is greater than or equal to 0 and is strictly less than k. Under this setting, direct computation shows that a to the power of m is congruent to a to the power of kq plus r. The first term in this product can be rewritten as a to the power of k, then to the power of q. Now let us use our assumption that a to the power of k is congruent to 1 modulo n. From there, we see that the first term in this product is simplified into 1 to the power of q, which is 1 itself. As a result, a to the power of m is congruent to a to the power of r modulo n. Notice how our computation has been simplified from m, whose amplitude might be really huge, to r, whose amplitude is at most k. So now the remaining question is, given the positive natural number n and the integer a, does such a k always exist? And if it does, how can we find such a k efficiently? In the rest of this section, we will restrict ourselves to a specific case that is relatively easier. That is, we assume that n is a prime number. In that case, this question can be answered by the Fermat theorem, which states the following. Let p be a prime number and a be an integer such that p does not divide a. Notice that since p is prime, this condition is equivalent to the coprimality of p and a. So under this assumption, we claim that a to the power of p minus 1 is congruent to 1 modulo p. In other words, the integer p minus 1 can serve as the desired exponent that we're looking for. Now let us discuss how to prove this theorem. To start with, we denote by up the set consisting of elements 1, 2, 3, 4 until p minus 1. The key ingredient of our proof is the construction of a function f from up to itself satisfying the following property, such that for an arbitrary integer k in up, the function value fk is congruent to the product of k and a modulo p. More precisely speaking, this function can be constructed in the following manner. Indeed, once we're given an integer k in up, we can multiply k by a and compute the value of their product ka, which will be an integer. Now, we can apply the division algorithm to the dividend ka and divisor p. This will produce a remainder rk that is congruent to ka modulo p. Moreover, we know that rk is greater than or equal to 0, strictly less than p. Now, notice that by our assumption, a is coprime to p. Moreover, since k is in up where the elements vary between 1 and p minus 1, k is also coprime to p. As a result, their product ka should also be coprime to p. In other words, rk cannot be equal to 0. From there, we see that rk must be a positive natural number between 1 and p minus 1. In other words, rk also belongs to the set up. Now in our construction, we can ask f to send k to rk. We do this for every k in up. Since each rk is between 1 and p minus 1, the function f thus constructed is indeed a function from up to itself. Finally, since rk is congruent to ka modulo p, so is fk. This finishes our desired construction. To see how this construction works more clearly, let us take an example where a is equal to 3 and p is equal to the prime 7. For instance, what should be the value of f1? Well, since in our context, a is equal to 3, we should first compute the integer 1 times 3, which is again 3 itself. Since 3 is already in the set U7, we define f1 to be 3 itself. Similarly, we can compute the value of f2. To this end, we first multiply 3 by 2, which gives 6. Since 6 is already in U7 itself, we set f2 to be 6. Keep going, let us compute f3. 3 times 3 is equal to 9. Although 9 is not in U7, 9 is congruent to 2, which is in U7. Thus, we set f3 to be 2. Similarly, 4 times 3 is equal to 12, which is congruent to 5 modulo 7, and we set f4 to be 5. Keep going from there, we compute f5, since 5 times 3 is equal to 15, which is congruent to 1 modulo 7, we set f5 to be 1. Finally, 6 times 3 is equal to 18, which is congruent to 4 modulo 7. Thus, we set f6 to be 4. In this way, our construction is finished, and we see clearly it is a function from U7 to U7 itself. Notice that actually the function we have constructed in this example is a bijection from U7 to U7 itself. This is indeed true in general. That is, we prove that for an arbitrary prime number p, the function f from up to itself constructed using the aforementioned method is bijective. We first prove the injectivity. To this end, let k1, k2 be two elements in up, where fk1 is equal to fk2. By our construction, this means that k1a is congruent to k2a modulo p. Recall that a is co-prime to p. Thus, it has a multiplicative inverse, namely a negative 1. Let us multiply a negative 1 on both hand sides, which implies that k1 is congruent to k2 modulo p. However, notice that both k1 and k2 are between 1 and p minus 1 because they are elements from up. Thus, the only possibility that they are congruent to each other is that they are identical to each other. This proves the injectivity. Next, for the surjectivity, let y be an arbitrary element from up. We can multiply y with the inverse of a whose existence has already been justified before. This gives us an integer that is still co-prime to p. Now, by the division algorithm, we know that we can find a k in up which is congruent to this product. By our construction, fk is congruent to k multiplying a, which is congruent to y multiplying a inverse multiplying a, which is in turn congruent to y modulo p. Since fk and y are both in up, if they are congruent to each other, they must be equal to each other. In other words, fk is equal to y, and the function is thus surjective. Great. Now that we have proved the bijectivity of f, we see that the set consisting of 1, 2, 3, 4 until p minus 1, and the set consisting of f1, f2, f3 until fp minus 1, they are the same sets, because both of them are up itself. Thus, the product of all elements on the left-hand side should be congruent to the product of all elements on the right-hand side. In other words, p minus 1 factorial should be congruent to the product of f1, f2, f3 until fp minus 1 modulo p. Yet recall that in our construction, fk is congruent to ka modulo p for any k in up. Thus, this product is also congruent to 1 times a multiplying 2 times a multiplying 3 times a, keep going until multiplying p minus 1 times a modulo p. Regrouping all coefficients together and all copies of a together, this product is congruent to p minus 1 factorial multiplying a to the power of p minus 1 modulo p. Finally, recall that by the Wilson theorem, since p is a prime number, p minus 1 factorial is congruent to negative 1 modulo p. Thus, by multiplying negative 1 on both hand sides, we finally obtained that a to the power of p minus 1 is congruent to 1 modulo p. This is precisely the desired identity. We have thus proved the Fermat-Little theorem. Let us end our discussion by applying the Fermat-Little theorem to the computation of 3 to the power of 2,026,102 modulo 7. Since 7 is a prime number and clearly 7 does not divide 3, the Fermat-Little theorem indicates that 3 to the power of 6 is congruent to 1 modulo 7. Now, by division algorithm, the original exponent can be written as 337,683 multiplying 6 plus 4. Thus, the original modular exponentiation can be simplified into 3 to the power of 6, again to the power of 337,683, multiplying 3 to the power of 4. Now, since 3 to the power of 6 is congruent to 1 modulo 7, the first term is simplified into 1. Thus, the original term is congruent to 3 to the power of 4, which is congruent to 4 modulo 7. You can see how such almost trivial application of the Fermat-Little theorem has greatly simplified our computation of modular exponentiation.